Hey everyone. So it's been a while since I've done a video like this, but recently a friend of mine reached out and asked if I would be able to uh, cover a particular physiology concept, an exercise physiology concept that's very commonly talked about. That concept is lactate threshold. I thought about it and figured, it wouldn't be a bad topic to go into. It'd be good to sort of stretch my brain and dig back into some of these concepts and also challenge my ability to explain them. Um, and it may help a few people out. So what this video will intend to be is just a very, very brief, very quick introduction to that. Now, before going into lactate threshold and explaining what it might be or how we might want to look at it, I need to explain or very briefly define another very closely related concept, and that is VO2 max. Now, it's closely related in the sense that the percentage of your VO2 max is used as sort of the x-axis or independent variable scale that we express lactate threshold along. And I'll explain what I mean by that in a bit if that was a bit confusing. But what is VO2 max? Well, the term VO2 refers to a volume of oxygen per unit time that is consumed by or used by the body. Broadly speaking, that's all it is. Now, we often talk about it in the context of exercise because these numbers go up significantly when we put the metabolic demands on our bodies that exercise will tend to impart. So we'll see it expressed as this. So I've written this out. Apologies for the reflection on my little screen or on my board here. But you'll see something like VO2 max, capitalization, slight variations in how it's punctuated sometimes. Don't get caught up in that. You'll sometimes see a notation that includes a dot over the V, which again refers to per unit time, in this context per minute. But again, this is saying, or this is expressing how much oxygen your body is actually able to extract or is extracting maximally. So what is the most oxygen that your tissues can extract per minute based on the demands that you put on the tissue and the abilities, or tissues rather, and the abilities of those tissues to work through aerobic pathways. And I'm not going to get into all the minutia there, but that's the general gist. And to determine what this is, we have two major components that we consider. So if I just put my equal sign here, there's an equation that we use to express VO2 max. And it consists of two elements. One is Q, cardiac output, which again, since it's a minute value, that is how many liters or how much blood we are pumping out of our heart and thus through our systemic circulation every minute, times, so I can put another dot here, something called AVO2 diff, and it stands for arteriovenous oxygen difference. There are a variety of different ways to write it out, but you'll often see something kind of like this. It'll be something like this, AVO2 diff. Sometimes it'll be fully written out as difference. Sometimes you'll see it in parentheses like this. But what we have here, ultimately, is a pair of factors that determine the two aspects or the two sides of oxygen extraction. And let's see if I can color code it here. If I can use one hand. I have markers up here. These aren't working as well. But we've got delivery. So that's this guy right here, right? And you know what? Let me switch to this one because these are actually finer tipped than they should be. Let me try. Let's hope there's still some ink in this, right? Yeah, that'll still work. So we've got delivery, because that's cardiac output. How much blood are you delivering to the tissues, right? Every minute. So we've got that. And we also have a second element of this equation. Let's see here. Is this guy? It's not terribly fine. Good. Extraction, right? So that's the second element here. The extraction. That is, how much oxygen do the tissues actually remove? So you can be pumping all kinds of blood through a tissue, and if the tissue doesn't need a whole lot of oxygen, it's not going to pull it out. But both of these can potentially limit the amount of total oxygen extraction or total oxygen utilization the body is capable of. I'm not going to go into specific factors that will influence that right now, but this is the basic concept of VO2 max. And at submaximal intensities, you still have some kind of equation here or some kind of relationship that where whatever your cardiac output is, it doesn't have to be maximal now, some submaximal cardiac output multiplied by some rate of oxygen extraction, and you get whatever the submaximal VO2 or submaximal oxygen consumption within your body is. And again, in the context of exercise, we are most concerned with what's happening at the muscle, right? So at skeletal muscle level, there is some oxygen extraction, certainly with the heart muscle as well. We can't ignore that if we want to account for everything. And there are other tissues throughout the body as well, the brain and certain organs. But generally speaking, it's skeletal muscle that's responsible for the biggest increase in oxygen extraction as we are circulating more blood through the body. So hopefully that makes some sense. And this equation here, this whole equation, is referred to as, so that's this whole thing here. Oh wow, this doesn't even want to work. Okay. So let's use a different guy. Let's use this one. This whole equation is known as the Fick equation. My sloppy handwriting there, right? It's all crooked because I'm writing sideways, but hopefully that makes some degree of sense, right? So the Fick equation just refers to at a given cardiac output level and a given oxygen extraction level, you can determine how much total oxygen is being extracted by the tissues. And once you get to a maximal amount of intensity that you can sustain, which is determined through a number of criteria whenever you test it, you get what's called a VO2 max, right? Or a VO2 peak. Depends on the circumstances and whether you're obtaining a true value. But that's the basic idea. And I want to note that if this extraction idea, why is it called a VO2 difference? Well, if you aren't familiar with that, if you've never been told what this is about, essentially what's happening is you have a certain amount of oxygen that's in the arteries as the blood is being delivered to the capillary beds where oxygen exchange or gas exchange occurs. And then you can measure the venous oxygen levels. So that's in the veins after gas exchange has occurred in those capillaries and blood is returning to the heart. And you look at the difference between when before you delivered the blood to those tissues and after. And that difference tells you, well, that's how much oxygen those tissues must have used. So that's the idea behind a VO2 difference right there. So this is the first part of this, and I'll do a subsequent video explaining lactate threshold now that this is out of the way.